So the today's topic is power system inertia and the measurement techniques. So the topic will cover basically the first we will have a quick overlook on the frequency control, then what is inertia, its in and its role in the frequency control, concept of center of inertia when we talk in terms of the large power system, and then with the role of inertia in the various stabilities, and we will have how the inertia impact, the impact on the inertia is there with the transition that is ongoing in the grid with the R integration. And we will learn about the why the inertia monitoring is important, and then we will talk about shortly on the inertia, the estimation method, which can be online and offline. So let me just start with the topic on the quickly on the introduction to the frequency control and inertia and its role in frequency control. So we all know that the power system frequency, basically it is the rate at which the alternating current changes its direction, right? So, and it is defined for the AC power system only. There is no frequency concept in the DC power system. And AC power system has generally its designated frequency, which is basically defines the equipments, basically how the equipments are designed. In India, it is 50 hertz, USA 60 hertz. So there are many countries having 50 hertz, many countries having 60 hertz system. And there can be only one frequency in a power system. And it basically, it's like a heartbeat of power system that ensure that everyone is running in synchronism with each other. And it also ensures that whenever there is a variation in the supply and demand, then the variation in the frequency shows that particular the gap in the demand and supply side. So this is just a quick means whenever there is a frequency, the band is there, and we look into the what are the different type of band and the thing means limits that are introduced in the form of in the power system or in and associated grid codes for the overall design of the any of the power system. So you can see that whenever the generation is less, then we have a drop in the frequency. We have to increase the generation, and whenever there is an increase in the load, we have a higher frequency side, and we have to reduce the generation, or if there is a possibility, the increase in the load should be there. So the frequency limits, there are different kind of frequency limit in the power system. Let us talk about the Indian power system. We have our system is designed to run at 50 hertz, and we have an inherent dead band for for the dead band are basically for the different controllers that act in the power system, and that is plus minus 0.03 hertz. And then we have an operational range, which is very important for the system operator and for the safe power system operation, and it is basically 49.9 to 50.05 hertz. And then these are basically for the basically designed that our all frequency control action are basically designed in that particular range. And then we have emergency range. Basically, these are the equipment design limit for Indian power system 47.5 to 52 hertz. Many places it can go to 47 hertz to 52 hertz. And you can see on the right hand side, we have the different, frequencies and their limits for the different power system across the world. So there can be, large and small frequency deviation that is always ongoing in the power system. Okay. So smaller frequency deviation generally occurs when there is a small mismatch in the generation and load due to the fluctuation in the electricity consumption, changes in the energy resources, or any kind of deviation that we observe due to, renewables are there. So there can be some weather parameter change, that can be change in the load also due to the weather changes. So those kind of events triggers minor variation in the frequency. And such a small variation in the frequency, there is a power system inertia in this, and that dampens such kind of frequency variation. So keep the frequency within the dead band. And there can be large variation also in the power system, and the frequency can deviate from its nominal frequency, frequency, that is 50 hertz, and it can deviate, it can go to a very lower frequency range depending upon the size of the contingency. So it is going beyond your operating range basically. And for that, if it is going beyond the operating range, then system responds with different kind of control action, which we call frequency control action. And with these frequency control action, frequency is tried to it is restored back to the original nominal frequency. So we'll look into the what are the kind of let us understand on the aspect of large frequency deviation and control. So you can see one. Let me just Yeah. So if there is a tripping in the system of any particular generating plant, so we have lost some generation in the system, then at that point of time frequency starts to fall, and then it's means when the that frequency will start falling, and then there will be a certain rate of change of frequency, that what we call as a RoCoF, and with that particular change the frequency is starting to falling, and with that the system first respond with whatever the inherent controls are there, which are basically whenever there is a change in frequency, those control act. So if those kind of inherent controls response will come into the system to means it is basically to restore the frequency, reduce the rate of change of frequency, and then it reaches the lowest point where the balance is there between the load and generation, and then after that frequency starts recovering through the various control measures. And you can add means because we have a generation loss, so you have to means to balance that particular generation loss, you have to introduce the similar amount of generation into the system or reduce the similar amount of load into the system so that frequency can go back to the nominal frequency. So what are the frequency control actions that are available in the power system, and how they respond towards whenever there is a major generation loss? So these are basically any power system has generally a 5-stage process, also called as a frequency control mechanism. So leaving apart the first one, that electromagnetic energy stage, the inertial response, load damping, and governor response. These are the three that are first to act, that are we call as a primary frequency response. And there is a automatic generation control, which we call as a secondary frequency response. And there is a tertiary control, which we call, which can be achieved through the economic dispatch, and we call it as a tertiary frequency response. So these three frequency response, different kind of frequency response is meant to control the frequency. And in case frequency, if it goes beyond a certain limit, it is going towards the emergency limits, basically. And this is means due to a large generation loss, then in that case frequency can fall beyond certain levels, and recovering those things through this dispatch will take certainly a lot of amount of time. In those conditions we have emergency control in the form of under frequency load shedding relays and rate of change of frequency relays, basically, which sets certain amount of loads so that the frequency recovery can be quick, and it should not go into the emergency range, basically. So now let us understand about our main topic, that is inertia. We talked about that when there is a small load generation variation, then power system inertia is there to damp such kind of load generation variation impact on the frequency. So what is inertia? In terms of physics, we know that it is the tendency of an object to maintain a state of rest or the uniform motion unless you put some external force to it to change its speed or the velocity or the angular velocity. Unless until you do that, it will keep try to maintain whatever the state is there for that particular object. So in classical physics, we read about the linear motion, we have rotational motion. So in linear motion, what terms of inertia we call as the physical mass of the object that determines its inertia. And it's it tells us how difficult it is to change the linear velocity of the object around a linear path. Similarly, in case of rotational motion, we have moment of inertia, and it is analogous to the mass in linear motion, and it tells us how difficult it is to change the rotational velocity of the object around a given rotational axis. Then let us come back to the power system inertia. So we know that in the power system we have multiple kind of energy conversion going on. So first is the kinetic energy conversion of generator, that is the motion of a steam, gas, or wind turbine that we see, and it is converted to the electromagnetic energy. And there is another side of it that we have the right now IBR based inverter resources also. So those basically wind, like the wind plant, type 4 wind plant is there, then solar power plants are there, battery energy storage is there. So basically these converts the wind, solar, and chemical energy into the electromagnetic energy. So now we know that from the first point that we have rotating component in the power system. So they have the angular velocity. Okay, So, and they are synchronized. What are the rotating components that we have, like synchronous generation, induction motor, synchronous and induction generators are there. So, to means these kind of component equipments are there in the power system, which are synchronized with the system, and they are running at some constant speed, basically, or constant angular velocity, we say. And all these have kinetic energy in the form of their turbine due to the rotational motion at certain fixed speed. So we have various large masses in the power system and that are running at constant angular speed. And when we try to, means if the so much of mass is running at some constant angular speed and it's a mechanical speed and the mass is there, so very high inertia will be there. So it is not very easy to slow down the things when things are changing in the electrical side. And it is not that easy to change the, the speed of the things on the mechanical side. It will take a lot of effort. And that effort that we see and that the challenge means, the response that we see, we call it as an inertial response in the system. So we have many electrical, means rotating equipments, and those are directly coupled, right, in the power system. And these are coupled through the electromechanical coupling, basically. We call a locked rotor condition. And any impact on the power system on the electrical side, let us, we have a two side in the power system. One is on the mechanical side, that is the turbine side, and one is the electrical side, that is the generator side, right? So we have P electrical on that and electrical torque and electrical power on one side, and we have P mechanical input and the mechanical torque, which are in opposition with each other, because one is trying to means oppose the other so that they have a balance and the energy is being converted from one source to the another source. So they will always be in a position and in balance condition. That's how the frequency keep on 50 hertz basically. And if, means if you do any change in the electrical side, then there will be an imbalance between the electrical and mechanical torque in the system. And due to that imbalance, what will happen is that there will be a change in the mechanical torque will be there. So speed of the generator will try to reduce. And at that point, it may increase also. So at that point of time, inertia will come into the play, the inertia of that particular turbine and the generator combined motion. And that will try to resist this change in the speed, basically. And that's provide the concept of power system inertia, which resists any change in its frequency. And like on the frequency we call on the electrical side or its angular speed on the mechanical side. This is the concept of inertia in power system. So what basically is happening in terms of the inertia whenever there is a, tripping of any generator or loss of any load, is there higher frequency, the lower frequency due to the generation loss or higher frequency due to the load losses there. So what actually happens in power system? So these rotating generator and motors, which are synchronously connected to the power system, has stored kinetic energy. And after any kind of contingency event, like the generation tripping, this stored energy will be drawn. Basically, the stored energy will be drawn from these generators to maintain the balance between the production and consumption. So that's the law of conservation of energy. And this stored energy, when we draw, we call it as an inertial response, basically. So however, you know that mechanical power input to generator is not going to change immediately. It has to take a lot of, means it is going to the fuel has to increase, the pressure in the steam turbine has to be released so that it can try to resist. So generator will eventually start to slow down and system frequency decline as a result. And this rate of change of this decline of the speed basically depend upon the amount of inertial response available at the time of event, basically. And if we talk about any particular generator, so how this kinetic energy is stored, what is the concept of inertia? So just in simple word, you can explain it like this, is that, and if you start any particular generator, so it has to, first you have we know that what should be the speed of the generator to produce a 50 hertz kind of electrical signal on the other side. From mechanical, what should be the mechanical speed to provide the electrical frequency of 50 hertz. So we know that the formula is already there. So what we know that let us say it is a 1500 RPM machine. So first you try to run the machine through, through that the turbine will provide that much amount of enough pressure in the form of a steam, or it can be in the form of water. So any kind of fuel will be there that will burn and provide that much of input to the turbine, basically. Turbine will start rotating. It will reach a speed at which the electrical and mechanical frequency can be equal on each other side, the energy conversion. So this particular, means you are making the turbine to run at such a high speed. So the turbine has a significant amount of mass will be there. and it is running at, let us say, 1500 rpm. So this will have the angular speed of this 1500 rpm, and then it has its own mass. So then we know that high omega square, that will be the whatever the kinetic energy that is being stored in the particular turbine, sorry, the combined turbine and generator system. So now it is not producing any energy. It is just consuming the energy to run first at 1500 rpm. And then as you synchronize this particular, let us say it is a 1000 megawatt machine is there, which has the capacity of 1000 megawatt. It may take around 30 or 40 megawatt basically for running that much of energy, kinetic energy, that much of kinetic energy will be there in the machine to first run at 1500 rpm, not producing any electrical energy. This 40 megawatt is just to run the machine at that particular speed. So this, whatever the kinetic energy that is just stored extra over there. So this kinetic energy, if you try to extract and produce the same rated change of, means the same rated power, this particular, if you multiply the rating of the machine into some time and you consuming this much of mechanical energy, if there is no, means there is no, on the electrical side, there is a requirement of energy, then this 40 megawatt, let us say 40, means 40 megawatt is there and running the machine at this particular speed. Then this particular 40 megawatt, if we can extract in how much amount of time, that basically decides the inertia, and that we basically represent in terms of some seconds basically. So we multiply this stored in kinetic energy, you have the stored kinetic energy and the rated machine, then you multiply it by that time, the time at which this will utilize its kinetic energy only to produce the rated power, that particular generator. Then that particular time, the time constant that we have, we assume it as an inertia constant for that machine. That's why the inertia constant, means basically the unit that we use is basically seconds in power system basically. So what are the contribution on the types of inertia and the contributing factors? So first is the synchronous inertia. We talked about it. It is coming from rotating generators and motor. You can see this one. And this basically inherently respond because they are electrically coupled, electromechanically coupled with the system. So whenever there is a change in the frequency, then it will start. Inherently, it will immediately respond to the system. And there is no delay in this particular response. When we have a concept of synthetic inertia or fast frequency response, these are basically for the inverter-based devices, IBR-based renewable energy or the battery energy storage that we have. Basically sense the frequency fall on the system or the point of connection, and they will take basically the voltage from the point of or the wherever they are connected to the grid and see based on the frequency, they will calculate the frequency. If they see there is a decline in the frequency or there is a rise in the frequency, accordingly to that, they will respond with certain kind of droop characteristics basically. So that what we call as a fast frequency response. So they will be entirely dependent on the system frequency. If there is a problem with the voltage or any kind of means any transient in the voltage on the system frequency is there or wherever they are connected, it will certainly there it is going to impact the fast frequency response also. So that's why these are slightly delayed. They are not inherent. They will be slightly delayed so that they get a very stable kind of voltage basically. Then we have a concept now that is coming with the grid forming inverters. That is the concept of virtual inertia. Basically, you mimic the system, you mimic your IBR in the form that they respond according to the requirement of the they respond according to the any kind of synchronous generator basically. So you just mimic the IBR basically so that they can respond according to the whatever it will check its internal voltage, because grid forming inverters will have their own voltage source, internal voltage, and they will see the system voltage and how the system internal, what are the angular changes are there. And based on that, they will try to provide the similar kind of response that the synchronous inertia is providing. However, it will be slightly delayed compared to the synchronous, because synchronous, it doesn't take time because there is a electromechanical coupling in there. Virtual inertia, certainly there will be inverter will be there, so slight delay is there. So in generally, what has been observed is that virtual inertia basically comes into picture around 200 milliseconds. And the synthetic energy generally comes, the guidelines are there in the grid code, it is around 600 milliseconds. So let us quickly go, let's skip this one. So we have the typical inertia contribution from the different kind of power plants shown here. So overall inertia constant of any machine depends on its dimension, geometry, mass of the rotating part, rotational speed of the machine, MVA rating, and generation technology also. So inertia of overall power system, what we mean is that it is the complete system. We were talking about initially individual generator capability. In terms of the system, it is the capability of all the combined generators in the system, its ability to resist the change in the frequency whenever there is a disruption in the balance between load and generation. So these are coming from different sources. Now we have talked about it, synchronous machine. There will be a load damping also. Load side response is there because frequency depends. There are frequency dependent load also, right? So if there is a change in the frequency, if there is a fall in frequency, they may consume less. If there is a rise in frequency, they may consume more. What we terms in the power system, we call it as a load damping factor. And then we have responses from IBR and other grid elements can be there, which are now coming like synchronous condensation and in the grid forming inverters and all this. So, but right now the predominant source of inertia in our system is the synchronous generator.